in the last couple of classes, we had been looking at the spectral density function, which is a major tool in analyzing time series in the frequency domain. However, we need to know the spectral density function from a given series. So, we need to estimate the spectrum as such. What we will do today is to look at what is referred to as the periodogram analysis, where the periodogram actually represents the spectrum. So, it is a sample version of the spectrum, but it is a very crude version of the spectrum, and hence we will subsequently see how we can refine the periodogram to get a better version of an estimator for the spectral density function. To look at the periodogram, let us begin with the data. So, we have x t, which is observed at time t equal to 0, 1 to n minus 1, and we will be looking at the frequencies omega j, which are twice pi j by n, where j runs from 0 to ln. And this omega j's, as you can see, is that if the first one is twice pi 1 by n, then you have twice pi 2 by n. Of course, the first one is 0, and you go on subsequently. So, they are equispaced frequencies. And what is ln? Ln is the largest integer contained in n by 2. That is, if n is even, then ln obviously is n by 2 itself, but if n is odd, then ln is n minus 1 by 2. Now, since there are n observed time points, we can only define n underlying sinusoidal curves to represent x t. So, what we are assuming is that we have n points and we are taking n frequencies, equispaced frequencies, and building up sinusoidal curves based on these frequencies. Since these frequencies are given to us, their coefficients will be unknown in general, the amplitudes, and hence we will need to estimate them. So, we cannot exceed the number n. So, we will take as many as n frequencies and the corresponding amplitudes. Now, before we come to this model, let us consider the orthogonal functions. So, cos omega j t is cos twice pi j t by n in our case, and similarly we will be looking at the functions sin omega j t, which is sin twice pi j t by n. Notice something here, that sin omega j t is equal to 0 when j is equal to 0, because in this case you have sin 0, and if n is even, in that case when j is equal to n by 2, in that case it becomes simply pi t and it becomes again 0. So, in this case you have these two sine functions equal to 0. Thus, there are always going to be n non-zero functions. Mind you, if you have an even number, then you have actually n plus 1 into 2 functions, of which 2 are going to be 0, the two sine functions at the two extreme ends. And if you have an odd number, then one of the sine functions is going to be 0 and the remaining n functions will always be non-zero. So, we will always have n non-zero functions as the basic underlying structure. So, let us model with ut as the zero mean error term, and in that case we will express x t as sum over j equal to 0 to ln a j cos omega j t plus b j sin omega j t plus ut. So, what we are looking at now is a combination of the orthogonal functions cos omega j t and sin omega j t with this coefficients aj and bj, which would generally be unknown. We will have a look at what these coefficients are, but we will assume for the time being that these are unknown, and we make a composition of this, and this generates xt. Of course, there would be an error involved, which would be ut, and our purpose would be to get aj and bj by minimizing this error. But before that, let us look at a lemma which would be required to actually get aj and bj. So, the lemma states that for jk for 0, 1 to ln, if we have two cost functions, then the product of these two for twice by j by n and twice by k by n summed over t would be equal to n if j and k are equal and equal to 0, or n by 2, would be n by 2 if j k are equal but not equal to 0 or n by 2, and would be 0 if j and k are not equal to each other. Whereas for the sine functions, this two product of the sine functions summed over t again, this would be n by 2 if j is equal to k, but they are not equal to 0 or n by 2. We have seen that if either one of them is 0, then the sine function would be 0 for 0 and n by 2 for these two values, and hence those two does not come, and it is always going to be 0 if j is not equal to k. As for the cos into the sine function summed over t, this is always going to be 0 whatever your j or k is, whether they are equal or unequal. Now, given this result, let us minimize summation ut square, which is xt minus sum over j aj cos omega j t plus bj sin omega j t, and then you square this whole thing up and sum over t. And if we use the lemma, then the aj's come out to be 2 by n summation xt cos omega j t, provided j is equal to 1 to ln minus 1, and it is 1 by n into the same quantity. So, it is just the coefficient is different if j is equal to 0, and if we have even number of observations, in that case for n by 2 as well. bj's always come out to be 2 by n summation xt sin omega j t, and these aj's and bj's are referred to as the Fourier coefficients. Now, once we have got this Fourier coefficients, now let us look at what the sum of squares comes out to be. First of all, you can see that x bar is equal to a naught. If you go to the expression of a naught, aj in this case, and you will see that if you take j equal to 0, you get x bar. Then using the lemma, we can show that summation over t x t minus x bar square, which actually is the total variability, it is the variance into the number of observations. So, it is n times the variance, and this comes out to be equal to n by 2 summation for j equal to 1 to ln aj square plus bj square, and we will call this n by 2 aj square plus bj square as I omega j or I n omega j at times, and this is basically the sum of this I n omega j's. We refer to this I n omega j's for j equal to 1 to ln as the periodogram. Also, I n omega j can be written as 2 by n into this expression, and now you notice that we are not using the expressions for aj and bj. So, we substitute the aj's and bj's, again use the lemma, and you can write it in this form, where this is in terms of the original variables xt's. So, you can write the periodogram in terms of the original variables. You can derive it directly from the original variables. You do not need to go to the estimation of the AJs and the BJs to get the periodogram. Now, how does this help us? So, we saw that the total S's can be written as the sum of the periodograms. And if we write this out in a ANOVA type of table, then we have the different sources. The mean with 1 degree of freedom, and it has a sum of squares which is n times a naught square. So, the x bar was a naught, and if you square this, the sum of squares if you are looking at, it will be n a naught square. And more importantly, if you look at the omega 1, which is the first frequency, then it is equal to twice pi by n. It has 2 degrees of freedom. It is given by n times a1 square plus v1 square by 2. Similarly, omega equal to 2 would be having 2 degrees of freedom, and it is again given by n times a2 square plus v2 square by 2, and so on and so forth. And the sum of this would come out to be summation xt square. So, mind you, the way we derived it, it was the total minus the mean. So, if you take the first mean out, that is, if you take xt square, xt minus x bar square, then you leave out the mean degree of freedom, then the total degree of freedom becomes n minus 1, and you split it up into the different components frequencies. So, you break it up into the frequencies omega 1, omega 2, omega ln, and now you see that the sum of squares or the periodograms are the sum of squares. So, the periodogram tells you which of these frequencies contributes most to the variability. So, if you have a large value somewhere, say maybe omega 2 has a large value, which is n a2 square plus b2 square by 2, then we know that this frequency plays a dominant role in expressing the process that we are looking at. So, this is how we can identify the frequencies which are major players in expressing the corresponding process. Now, this I in omega j is obtained only at the points omega j is equal to twice pi j by n. So, it is not smooth, it is just very discrete specific values. So, if you want to define it for all omega, there is a very crude way of doing it. What we do is we take I n omega to be equal to I n omega j if omega lies in the interval twice j minus 1 into pi by n to twice j plus 1 into pi by n. So, basically we have a terraced function. So, at each omega j, we basically extend this I value on either side as a straight line, as a line parallel to the horizontal axis, and depending on at which level we are, we get a flat line. Okay. So, the differences between the 2 points is exactly divided, half of this goes to one point, half to the other point, and you get a horizontal line. So, it looks like some sort of a terraced type of thing, sometimes going up, sometimes going down. However, as n becomes large, mind you that twice pi j by n values, it becomes smaller and smaller, they tend to each other, come closer and closer, and hence this function would become smoother and smoother. Hence, for large n, we will have a very smooth function. The problem with the periodogram is that for a weakly stationary time series with an absolutely summable autocovariance function, I n omega by 4 pi is an asymptotically unbiased estimator of the spectrum, but the variance of I n omega by 4 pi does not go to 0 with n. So, it is unbiased asymptotically. So, you can take it as a estimator for f omega, but it does not go to, its variance does not go to 0 as n becomes large, which really means that it is going to be an inconsistent estimator. So, that is one of the major defects of the periodogram, and that is why we need to improve on the periodogram to get a estimator which would be consistent for the spectrum. Now, there are several ways for doing this, but all of these methods actually start with the periodogram itself. So, the periodogram gives an initial raw estimate of the spectrum, which can be smoothed, as we saw. We can improve on the smoothing as well, and which can be improved on otherwise as well. We will see how to get consistent estimators of the spectrum. So, we need to improve on the periodogram itself. But the other thing that this periodogram does is it gives us a rough idea of what the variability of the underlying process is. So, the spikes in the plot of the periodogram indicate the major frequencies that underlie the process, and hence the original series can be closely approximated by superimposition of the sinusoidal curves given by these frequencies. That means you pick up the major frequencies, the high frequencies, okay, the frequencies that contribute the most to the variability, that is wherever you have a large ordinate, and then you build up the curves, very smooth curves corresponding to these frequencies. And if you superimpose these curves using the coefficients, the Fourier coefficients, then you are going to come up very close to the original underlying process. Okay. So, that is how you can rebuild xt given the periodogram. How can you get a better estimator? Now, recall that gamma hat h is an estimator for gamma h. So, it is the sample version of the autocovariance function, and in that case I have in omega j, which I can write in terms of gamma hat. This is the periodogram in terms of the a.c.f. So, instead of in omega j, if I substitute the value with some weights Cj, say we take, instead of just gamma hat naught, we take C naught gamma hat naught, instead of gamma hat k, we take Ck gamma hat k. So, we can make a combination, weighted combination of this, where Cj's are weights and we just sum up to m. M is some truncation point, we will decide on what m is. So, instead of the original in omega j, we look at the new one here, which is in star omega j. And in this case, because the higher the a.c.f, the less efficiently it is estimated, because if you have a larger lag, you have less points to construct the a.c.f from. Because if you have n observations, then if h is equal to n minus 1, you have one single observation, the first and the nth, to get gamma n minus 1. So, the higher the value or the higher the order, the less efficient would be the estimator. So, in that case, you should be putting less weights on this, and also the higher values would have less effect, because as you move further away from each other, there will be less correlation and less weights are put. So, Cj should be decreasing, and what we assume here is that we take them to be 0 beyond some lag m. So, m can be chosen such that you have reasons to believe that beyond that the gamma h's do not have any relation between each other. Okay? So, they do not actually contribute. So, that is how you choose m. Now, once you have done this, the next thing is to choose the Ck's, and this is very often in time series terms or the frequency domain studies terms. They are called window carpentry. So, you have a window, that is, the window is up to m, that is the bandwidth, and in that case you choose your coefficients. We will not discuss this in great detail here, but we will give you two such windows which are very commonly used. One is Tukey's window, and that is given when Cj is equal to half 1 plus cos pi k by m, and the other, which is also very popular, is the Parsons window, which is a little bit more complex in that you define this differently for k which when it's less than m by 2 and for k when it's greater than m by 2. So, you have this type of, there are several other types of windows by which you can actually smooth out the series, and you can show that the resultant I n star would be consistent for the spectrum. So, this is an improvement, but remember that this is again based on the periodogram itself. It's just a modification of the periodogram. There are several other choices of the CJs. There is a huge literature on this, and there is also several other choices of consistent estimators, but we will be looking at them in our text, but we will not be discussing them here. But what we can say is that the periodogram actually is fundamental to the estimation of the spectrum, although it is inconsistent. In today's lecture, we studied the periodogram analysis. The periodogram is a tool to analyze the data in the frequency domain. It gives us a sample representation of the spectrum. Now, however, in this case, the periodogram is not a consistent estimator of the spectrum. Hence, we need to improve on it. We also saw how we can do that and obtain a consistent estimator for the spectrum from the raw periodogram that we get from the data. We also saw how the periodogram actually helps us to identify the frequencies or the sinusoidal curves that underlie a given process.